So here we are in Chapter 7, the quantum mechanical model of the atom. Chemistry is taught a lot of different ways and a lot of different times, and I think this is probably the best way to do it. Just jump right in with quantum mechanics. Um, Sometimes we spend a lot of effort learning about all the past models very intricately, and you probably know that I'm a pretty big fan of history, and I think that perspective is important. Um, But I think that we're in a transition area where we're spending less time on the Bohr model of the atom. We're really starting to move towards the quantum mechanical model of the atom, which is our current best fit model. Now, the old ones are important so that we recognize where we come from and we can build on the logic and the foundations of why these things occur. So, so determinism is an interesting philosophical concept. And it's one that you might have thought about before, because if we've told you that the universe is governed by rules, and that if you know the data, if you know a particle's position, if you know its velocity, if you know um, its momentum, really I should say rather than velocity, you know its momentum and its position, and you know all the other particles in the system, if you are a good enough mathematician, that you should be able to calculate out what the next moment would be like, what direction they're going in, what the results of any collisions would happen, and exactly what would occur. And then you know the next moment in time. And if you had a powerful enough calculator and you had all the information necessary, you should be able to calculate each moment in procession until you had calculated out all of everything. Now, some people would say that the main issue with this is purely one of information, that you can't know that. That if you could, you'd be able to do those calculations, but one, you wouldn't be able to gather that much information, because by the time you gathered information about the first few particles, the next ones would be different. By the time you gather information about those, the first ones would be different. Other people would say that the problem was with the calculator, that we don't have that level of calculation yet. But still, determinism proves an interesting philosophical issue as it relates to free will. Um, but if we go back in history, I said the scientists used to be named natural philosophers, and so there have been a lot of big names same in this same field almost. Albert Einstein, the most well-known name of all of them, but not necessarily the most important. Niels Bohr, Louis de Broglie, Max Planck, Werner Heisenberg, Paul Dirac, and Erwin Schrödinger. So quantum mechanics forms the foundation of chemistry, and a lot of the things that we've explained all come from quantum mechanics. It explains the periodic table, the behavior of elements, the practical basis for all kinds of stuff that we do. Um, Electrons are extraordinarily important here. And it's strange because we're talking about a different world than we live in. You and I live what we're going to call the macroscopic world. Macro meaning large, and scopic meaning the scale that we're talking about. In the microscopic world, which is really the subject of chemistry, and microscopic versus macroscopic really details much of the differences between chemistry and physics, at least at this level. Um, Electrons are really small. Uh, so incredibly small. A single speck of dust is more electrons than other people have ever lived on Earth. Not just currently, but ever. And, the mind has a hard time talking about numbers this big because they get distracting. We get to a point where, I can't conceptualize any difference in my mind between 25 billion and, 3 trillion. At that point, they're just really, really big. And so a single speck of dust with more electrons than people have ever lived on Earth, it's just mind-blowingly big. I think is really most accurate way we can say anything about it. Mind-blowing. So the behavior of all these electrons is really what's giving us the behavior of the atom as a whole. The problem is we can't directly observe these electrons. And our information is largely based on observation. But in chemistry, we're not able to do direct observation. We have to do indirect observation. Because the problem is that the small size of the electron, its tiny mass, means that very small amounts of energy can have very large effects on its momentum. And this idea here is going to come up to be hugely important. Even shining a light on the electron would affect it very significantly. So this theory is meant to explain the behavior of our atoms. First, let's talk about light. Now, hopefully you got through this pretty quickly because of your previous knowledge of physics. Maybe we'll get slightly more complicated. I don't know how far you got into it. When we say light is electromagnetic, we mean that it's an electric field and a magnetic field. Now, they are orthogonal to each other, and they kind of cause each other. Now, they move through a constant speed in a vacuum. They will move at different speeds in different mediums, but in a vacuum, they are roughly 3 times 10 to the 8th meters per second. Now, I say that they're in different planes, so that as the electric field moves this way, we know that a change in an electric field causes a magnetic field, and a change in a magnetic field causes an electric field. So I say in some ways this is a self-sustaining change. Well, that sounds almost eternal, so the starting point was electron transition. Now, amplitude's a funny thing. We talk about analogies a lot, and analogies are wonderful. The problem is understanding the extent of the analogy and where it works and where it fails to work. So we give this analogy with these electromagnetic waves to the mechanical wave, and with good reason, because they share a lot of similarities. So when we talk about amplitude, we talk about height. Now, height makes a lot of sense when we're talking about a wave in the ocean. Height makes significantly less sense when we talk about sound or when we talk about light, because there's not really a height there. Intensity is much more descriptive. A higher amplitude of light means a brighter light. A higher amplitude of sound means a louder sound. Wavelength, represented by our fun little Greek letter there, lambda, is a measure of the distance covered by the wave. Now, when I say the distance covered by the wave, that means it's a single cycle, from one trough to the next, one crest to the next, from one node to the next. Just one cycle. How much distance do you need to complete one cycle? A very basic diagram. Frequency is given by the number of waves that pass a point in a given period of time. Now, we give that in hertz, which is kind of a weird, it's an inverse second negative first. The total energy is proportional to the amplitude of the waves and the frequency. So that means the larger the amplitude, the more force, the more intense it is. And the more frequently the waves strike, the more total force there is. There's definitely some analogy there to be formed with pressure, which we talked about. So the shorter the wavelength, the more frequently they pass. Since we're talking about electromagnetic waves, they're all moving at the speed of light, 3 times 10 to the 8th meters per second. So it means if you're traveling at 3 times 10 to the 8th meters per second, if you have a really long wavelength, you should not pass very frequently, and vice versa. Whenever we talk about the speed of light, we use this variable c, and c is our speed. Don't be confused by this Greek letter here. It looks like a V. We commonly use that instead of the F for frequency. Why? Well, why not? So C is a constant, so it gives us a relationship that if we know either the wavelength or the frequency, because we know the speed of light, we can determine the other. And because wavelength and frequency can be used to determine each other, it's hard to say what determines the color of light. Is the color of light depend on the wavelength or the frequency? Well, it's either one, just depending on which one you measure. Now, the problem with this slide right here is that we're talking about white light. We need to be really clear about that. It's not just light, it's white light. And when we say white light, we're already implying something else, visible light. We're specifically not determining something about light itself. We're talking about our eyes. It's white light is what our eyes can absorb, which is directly related to our ability of observation. So of the portion of light that we can absorb with our eyes, we can distinguish 7 clear colors: red, orange, yellow, green, blue, indigo, violet. The common acronym being ROY, G, VIV. When an object absorbs some of the wavelengths of white light and reflects others, it appears colored. So that, if, this person here is wearing this red shirt, white light hits it, which is composed of all the colors, red is reflected, that means it's absorbing orange, yellow, green, blue, indigo, and violet. So amplitude means brightness. So low amplitude's dim, high amplitude's bright. It's important to remember that visible light isn't a special kind of light. There really is no inherent separation between what's radio wave light and what's gamma ray light and what's visible wave light. The only separations we made there are separations that we called it ourselves. The electromagnetic spectrum is a full spectrum all the way from high to low, and it's continuous all the way between. We only carve out a section and call it visible because that's what our eyes have. If, we were bees, and we were for some reason highly intelligent bees that could record YouTube lectures, we would talk about visible light, but it would be a different range of frequencies than what humans would call visible light, just because based on a different kind of observation. Bees see higher into the ultraviolet, I believe. And so our radio wave light has the lowest energy, where our gamma ray light has the highest energy. Again, these are just our names. Means that gamma rays have an incredibly short wavelength, whereas radio waves have a very long wavelength. The higher energy they have, the higher frequency, like gamma rays, they can be potentially damaging to biological molecules. We call them ionizing radiation because it's radiation that can create ions. Now, don't let them demonize radiation too much, because radiation is also extraordinarily useful, and that it's what keeps the surface of our planet warm. So radiation doesn't mean bad; it's just a thing. So if you really try to think about, you've all seen this diagram. If you really try to think about what some of this stuff means in terms of size, like, if we look at the radio wave, for example, the FM radio goes all the way from, down to half a meter, all the let's see, here it'd be 1 meter. So 1 meter is already a very significant wavelength. When we start getting all the way down here, we're talking about very, very, very tiny pieces. But some, AM radio, you can get from so much further away. Because look at this huge wavelength just for one cycle. The thermal imaging uses infrared light, and we were probably way too vague when we explained this before. The fact of the matter is that all things that have energy, that have any kind of energy, will emit light in what we call black body radiation. All things do this. It just so happens to be that what we call warm in our macroscopic human world, the range of our body temperatures and slightly above that, the range of light that they give off just happens to be infrared. Now, things below that will give off, lower energy light, and the higher your temperature is, the more energetic light you can give off. Think about if you have an electric stove, think about when you turn it on. If you put your hand near it, you can start to sense the infrared light being given off. But if you wait long enough, not only can your hand absorb the infrared light, but eventually it'll get to a higher temperature and higher frequencies of light will be given off, and you'll start to see red light. You could say it'll be glowing red hot. Now, this is actually the process by which our sun emits light. It's so hot it's emitting all the way into these much higher wavelengths, primarily concentrated in visible light. There's a reason our eyes have evolved to absorb that spectrum, because our sun gives off quite a bit of it. But, our sun gives off all the way into the ultraviolet and beyond. We make good use of this, the high energy ones, to destroy tumors with ionizing radiation, trying to minimize the exposure of healthy cells and maximum exposure of cancerous cells. We've been doing radiation treatment for quite a while. The technological capacity that we're at today is amazing. Baylor has these two machines. They call it a gamma knife, is how they describe it. That's their marketing name. And they put you in this big room on this table, and they shine little lasers, lines of gamma radiation. And each one individually is weak enough that they'll pass through any cell without much issue. But they overlap them from different angles going all across so that they all converge on where the tumor's at. So all the healthy tissue that only one line would go through, one wave, a series of waves, one laser would go through, is inconsequential. But when they all meet at the one point, the tumor receives a highly concentrated dosage. What's interesting is they can move and adapt. I believe they still use gold, because gold shows up really easy on their imaging software. They implant a nugget of gold in front and behind the tumor, and that way, even as you breathe or even as your heart beats, as your body moves, the machine moves with it. It's really, like many things in science, quite clever. We talked about interference, and so this is what I'm talking about now. Constructive interference. When waves interact, to make larger waves called in phase, they're in destructive interference, they're out of phase. So if we look at the combination of these two waves, the crest to crest and trough to trough, we get constructive interference. We increase the amplitude, and the opposite when we get crest to trough, trough to crest, destructive interference. It's a common misconception. These two waves don't actually add up and combine. For example, in destructive interference, both waves are currently present, they're just not observed. Those two waves can still separate afterwards, and the waves still exist, they're just not being observed. Again, if we do an analogy with water waves, as one particle vibrates up and another particle vibrates down, we have these two waves. As the crest of one tries to push a water molecule up, and the trough, another wave, tries to push it down, it has, like a zero net force, but the forces are still there pushing in other directions. But we do see constructive and destructive interference with light, and that's what first got us thinking that it was a wave. Along with what we call diffraction. Diffraction is how we notice that waves will wrap around barriers, they'll move, and they'll bend. The diffraction of light through two slits gives us an interference pattern. It's an interference pattern. It's something we see with all waves and something we see with light waves. So if we have light and we shine it at a hole, it diffracts out. If we were, looking at, like sand being blown, sand, particles of sand would travel straight through. Waves diffract out. So this is a difference in wave behavior and particle behavior. So if we do this with light, we see these bands where we get constructive interference and destructive interference. And the constructive interference gives these very bright spots, and the destructive interference gives us very dark spots. So it was observed, now we're starting to get into really the quantum mechanics of it all. It was observed that many metals emit electrons when light shines on their surface. We call this the photoelectric effect, for obvious reasons. The classical wave theory attributed this effect to the light energy being transferred to the electron. The problem is, according to this theory, the wavelength of light is made shorter, or if the light's wave intensity made brighter, more electrons should be ejected. Remember that the energy of the wave is directly proportional to its frequency. The idea predicts that if a dim light were used, there would be a lag time before electrons were emitted, as it slowly builds up in energy. So you have light hitting it and electrons being pushed off. So that we can detect this by having this gap here. There's this metal surface, light hits it, the electrons should be pushed off and hit that terminal, and the electrons moving through it. It's current. But experimental observations, what we actually see is different. First of all, there's a minimum frequency. It doesn't matter how much light you have below that frequency, you will not get electrons to emit. That's the threshold. We have to surpass that threshold before we get any electrons emitted. And then we notice that beyond that high frequency light, that the higher the frequency of light, the faster that electrons be ejected. And this comes from Albert Einstein. He proposed that light energy was delivered to the atoms in packets called quanta, or photons. Quanta is a quantity, a small amount. And this is where the word quantum mechanics comes from. And there's a misconception that Einstein got the Nobel Prize for his work with relativity. The famous equation E equals mc squared. He has two theories, theory of special relativity and general relativity. But actually he got it for his work in quantum mechanics. It was the photoelectric effect and his descriptions there that give him his Nobel Prize. So the energy of a photon of light, just one piece of light, the smallest packet of light, this packet of energy, is directly proportional to its frequency. And we know that frequency is inversely proportional to wavelength. So the energy of a photon of light is directly proportional to frequency. That means the energy of a photon of light is inversely proportional to its wavelength. And there's a constant here. We call it Planck's constant after Max Planck. He gives this h here. And this shows up all over the place. Now the value is 6.626 times 10 to the negative 34 joule seconds, which works out to getting us from frequency to energy. Because remember that frequency is measured in hertz, which a hertz is a second to the negative first. So you do a joule second times an inverse second. The second and inverse second cancels out, leaving us joules, which is energy. So one photon at the threshold frequency gives the electron just enough energy for it to escape the atom. That's its binding energy. When irradiated with a shorter wavelength photon, a shorter wavelength means higher frequency, the electron absorbs more energy than is necessary to escape. So any extra energy above the energy it needs to escape becomes kinetic energy. This is the rate at how fast electrons are being ejected. So Suppose a metal will eject electrons from its surface when struck by yellow light. What will happen if the surface is struck with ultraviolet light? Now, ultraviolet light has a higher energy than that of yellow because it's a shorter wavelength and a higher frequency. So would it be no electrons would be ejected? Well, we're beyond the threshold. The threshold would be yellow. So if it exceeded the threshold, then yes, electrons would be ejected. So can't be number one. Number two says electrons would be ejected and they would have the same kinetic energy as those ejected by yellow light. Well, that would violate the law of conservation of energy, so that extra energy had to go somewhere. And in this case, number three is what would happen. The electrons would be ejected. They would have greater kinetic energy than those ejected by yellow light. The greater kinetic energy they would have would be the difference in energy between ultraviolet light and yellow light. So when atoms or molecules absorb energy, that energy is often released as light energy. That's what we see with fireworks. That's what we see with neon lights. That's what we see with all kinds of things. And this has been extremely useful in astronomy. This is how we identify most stars. We identify all stars. I guess size also comes into matter, but really it's their light. And we use this to identify a lot of atoms and a lot of molecules as well. So every element, because it has its own electron configuration, gives off different colors of light. And this same property is what's exploited to make fireworks. And so we use a prism or some kinds of ability to separate them out. What's important here, was important data that we observed, is that the light they emit is not continuous. It's a very specific wavelengths. We get these bands. Now I'm pointing at my screen as if you can see it. We get these bands here, and they correspond very specifically with electron shifts. So a white light spectrum that we see given off by something like blackbody radiation, like from the sun, that gives us a full continuous spectrum of, every wavelength and every frequency of everything in between there. But that would be for white light. For elements, they don't have white light entirely. Helium really basically has these 6. And barium has much more electrons because of a much higher atomic number. But you can still doesn't have that many. Oxygen and neon being different there, overlaid there in the white light spectrum. Mercury is an important one because that's what we use in our a lot of fluorescent lights. This is the difference in an emission versus absorption spectrum. It's overlaid there on a white light spectrum, just so you can see which band corresponds to which color. And emission spectrum, we're seeing all the things that are given off. For an absorption spectrum, we're seeing what would it take up. To give you an example of that, if we're looking at the light that a star gives off, it's emitting light, and we look at it with some kind of camera or something. We look at all the bands that it's given us. But say we want to look at dust that's in outer space. We have light pass through the dust, and that dust will pick up certain frequencies of light, and then those frequencies are missing because they're absorbed by something else. So they're opposites of each other. So Johannes Rydberg analyzed the spectrum of hydrogen and found it can be described with an equation that involved an inverse square of integers. So that means that the inverse of the wavelength is equal to a r, and it's the difference between the inverse square of m and the inverse square of n. And what's important here is that m was always an integer and n was always an integer, always a whole number. And so the fact that this relationship existed gave us a lot of data and information for going forward. So let's talk about our atom again. Remember our buddy Ernest Rutherford. He's the one who got the data using his very clever experiment with the gold foil that the atom contained a tiny dense center called the nucleus, and that the volume was about 1/10 trillionth the volume of the atom. That was extremely dense, and that the nucleus is essentially the entire mass of the atom. And so the nucleus takes up almost no space in the atom, but it takes up almost all the mass of the atom. And that it was positively charged, and that the electrons were somewhere outside of the nucleus. That's what Rutherford decided. Good to know. Some of the problems with Rutherford's nuclear model is that electrons are moving charged particles. From what we know of physics, moving charged particles give off energy. They create magnetic fields, for one. And that if they're giving off energy, then two things. That energy should be seen, given off as light or something else. And if the electrons are losing energy, then their orbit, they're moving around, should slow down, and they should crash into the nucleus. But they don't. So that means that the Rutherford model it's not fully explaining everything. The Bohr model, this is probably what you're almost taught entirely in as a sophomore, decided that the nuclear model of the atom does not explain what structural changes occur in the atom gains or loses energy. So we got energy levels, shells, so that the energy of the atom was quantized. This goes the same quanta that Albert Einstein was talking about, that there's only a specific packet, there's a specific amount of energy that it can give off. So that there's only, it's not a continuous spectrum. There's not just any energy that you consume, only particular amounts. So the electrons travel in orbits that are at a fixed distance from the nucleus. These are stationary states. The energy electron is proportional to the distance the orbit was from the nucleus. So this is where we talk about the shells. And the electrons emit radiation when they jump from an orbit with higher energy down to an orbit with lower energy. It means vice versa too. They absorb radiation when they jump from lower energy to higher energy. And this is based on their distance. And when we're talking about energy, the way this energy is being moved around is all with photons of light. So we're looking at a Bohr model of a hydrogen atom. So the N, that N equals 1, 2, 3, 4, 5, that's our orbital, our electron shell. So if the electron moves from, energy level 3 to energy level 2, that amount of light is 657 nanometers red. If we go from 4 to 2, that's 486 nanometers blue-green. From 5 to 2, that's violet. Now, it should make sense that violet has more energy, violet light has more energy than red light, and that should make sense because we look at the electron here is falling from the 5th level to the 2nd level. That should be a bigger energy discharge than going from the 3rd level to the 2nd level. Seems reasonable. Here's where things get a little crazy. Louis de Broglie, and that is how you pronounce it. It's not de Broglie, it's de Broglie. De Broglie proposed that particles could have wave-like behavior. We're starting to say, we talk about how wave behavior and particle behavior, it turns out that particles and waves are all the same things. It's just a matter of perspective. So de Broglie predicted that the wavelength of a particle, yes, particles have a wavelength, was inversely proportional to its momentum. But electrons are very small, so since they have a very low mass, their wavelength is significant. That means all things have a wavelength, which does seem weird. I know that you and I have wavelengths, that a car has a wavelength. But our extraordinary mass relative to an electron means that our wavelengths are insignificant, tiny, indetectable. The proof that the electron had wave nature came a few years later with the demonstration that a beam of electrons proves an interference pattern, same as waves do. So not only does light give this interference pattern, but if we have the detector of where an electron hits, the electrons do this too. So that means that electrons can behave like waves as well. The expectation, this was surprising. I believe the quote at the beginning of your chapter was, anyone who is not shocked by the predictions of quantum mechanics doesn't understand quantum mechanics. It's a quote by Niels Bohr. Because we would expect electrons, which we've talked about as these tiny spheres of mass, that they would behave the same way as if we had shot ping pong balls through these two slits, that we'd get two concentrated areas where they hit the target behind, and they don't. They tend to hit in some spots much more brighter than others. We get a constructive interference where they tend to hit, and destructive interference where they don't tend to hit. And it's even crazier is that it's not just the electrons interfering, it's not them reacting with each other. It's not just something about them both being negative and repelling or, something like that. Even if you fire one electron through, detect where it hits, then fire another electron through, detect where it hits, and do this one electron at a time, and then graph out the results, they still hit in the interference pattern. If we talk about the determinism again, determinism says that if you know all the information, you knew the rules, you could predict everything. Well, if we fire one electron, and then we fire another electron, even under the exact same circumstances, they don't necessarily hit in the same locations, which is strange. So here's what I was talking about, that if we were talking about particles, you should only get the two bright spots, but we don't. So observation becomes a problem when we're talking about these particles. When you try to observe the wave nature of the electron, you cannot observe its particle nature, and vice versa. Remember, it's both. Waves and particles are the same thing. So these are complementary properties. The more you know about one, the less you know about the other. So do we want to know more about its position, or do we want to know more about its momentum? Remember we said that the wavelength is inversely proportional to the momentum. And this is what's called Heisenberg's uncertainty principle. Yes, the same Heisenberg as Breaking Bad Heisenberg. So that the product of the uncertainties in both the position and the speed, momentum, was inversely proportional to its mass. So this means that the more accurately you know the position of a small particle, such as an electron, the less you know about its speed, and vice versa. This all has to do with the way that we look at things, with light. So electrons are very small. If we want to know exactly where an electron is, its location, we can only know the location of the electron in which cycle it's in. So we can only get it down pinpointed to a distance that's as small as the wavelength. We can just tell it's within this wavelength. We don't know what part of the wavelength it's in. So if we want to get a more precise reading of where the electron's at, we'll use an even smaller wavelength. The problem is, if you use a very small wavelength, short wavelength means high frequency, means high energy. So if we got a good read on its position, we use such a high energy light that we just gave this thing so much more energy, we now know nothing about its velocity because we've increased it. We gave it a lot of energy. Well, the problem is, if we want to try to figure out how much momentum it has, what its velocity was, we don't want to add very much energy to it. We're going to use a very, very, very low energy piece of light. That way we're adding an insignificant amount of energy to it. We're not really changing its velocity, and we can read what its velocity is. The problem is, if we use a very low energy piece of light, those low energy photons have a very long wavelength. And if we use a very long wavelength, then even though we might know its momentum very well, we don't actually know its location anymore. So it's a balancing act of how do we want to observe it and what level of precision do we want to know with position and velocity. And these experiments, the double slit experiment's an amazing experiment. I mean that literally. I mean, it really does amaze. So, according to classical physics, particles move in a path determined by the particle velocity, surface force, and active line. But the problem is that there's no way of knowing the position and velocity of an electron. Not both. No one or the other. So we cannot possibly predict the path. So it's indeterminate. There's an indefinite future. However, there are probabilities. So we can figure out probabilities and use statistics to figure out a lot of it. There's a really important law that our chapter actually doesn't talk about, really. It comes from Niels Bohr. Niels Bohr says that quantum mechanics, when we talk about them on the microscopic level, they might seem crazy. Counterintuitive, really, is what it means. But if you take these quantum mechanical predictions, and if you scale them up on the level that we observe in our world, they should match up with classical predictions. So, for example, on the right here, the probability of where a particle could be anywhere here, if we look at the average of all of it, where it's likely to be, we get our classical trajectory emerging. This kinetic energy formula is familiar to you. For an electron with a given energy, the best way to describe a region in the atom is high probability of finding it. And, so many things are related to energy. Now, it's beyond the scope of this course. I wore this shirt a little while back. Erwin Schrödinger. The Schrödinger equation, the math is far beyond the scope of our course. It's a very high-level math. It's a realm of calculus that we call differential equations. If you're in college to calculus 1, then calculus 2, then calculus 3, then you get into differential equations and linear algebra. Fun stuff. So Schrödinger's equation allows us to calculate the probability of finding an electron with a particular amount of energy at a particular location. So that Greek letter psi, the PSI psi, that's the wave function. That's what calculates out the wave. And this is the Hamiltonian, and energy is what the H and the E stand for, but we don't want to talk about the math. If we square psi and plot it versus distance, we start to get orbitals. We get probability is what we get. The square of psi, square of the wave function gives us probability. And we can distribute it to figure out where it's going to be at. Now, we can't go through all the math just yet, but as you do the math, if you solve out the function, you'll notice that there are certain numbers that start to emerge mathematically. And it was the math that made these predictions first. The math said that we should see these things, they should operate in this way. And then when we tested that against our observations, we found it to be consistent, even if it was counterintuitive at first. So we got these systems of integers. We call them the quantum numbers. There's actually more than just these three. There's also things like spin, for example. So n is our principal quantum number. You should be very familiar with n. N is what we've been talking about the shell. N equals 1, equals 2, equals 3, 4, 5. We looked at it just before on an earlier picture. We also have L, the angular momentum quantum number, and M sub L, the magnetic quantum number. Now, the principal quantum number, n, characterizes the energy of the electron in a particular orbital. It corresponds to Bohr's energy level. So the values of n that are acceptable is any integer greater than or less than 1. 1 is the minimum, and we can step up in energy values from there. The larger the value of n, the more energy the orbital has. Energies are defined as being negative. An electron would have an energy of 0 when it escapes the atom. The larger the value of n, the larger the orbital. And as n gets larger, the amount of energy between the orbital gets smaller. So that means the difference between n equals 1 and n equals 2 is greater than n equals 2 and n equals 3. They start to shrink up, as you see here. And this is just part of the statistical distribution. The angular momentum quantum number determines the shape of the orbital. And I think I referenced before in class that geometry is shockingly important, disturbingly so for some of us. When I first encountered it, I wasn't crazy about geometry either. I wouldn't be surprised if you weren't as well. Some people find it a nice relief from a year in algebra. But geometry is shockingly important, not only in chemistry and physics, but even so in biology. So the values of L are accepted anywhere from 0 all the way to n minus 1. Meaning if we're talking about, a shell that, if the quantum number n is 3, then our values of L can be 0, 1, and 2. So each value of L is called by a particular letter that designates the shape of the orbital. So we have different types of orbitals: s orbitals, p orbitals, d orbitals, and f orbitals. And these align with our periodic table. The magnetic quantum number, m sub L, is an energy that specifies the orientation of the orbital. So it's the direction in space the orbitals align relative to the other orbitals. Now it's m sub L because values are integers from negative L to positive L. And this includes 0. So for example, if L equals 2, then the values of m sub L that are possible are negative 2, negative 1, 0, positive 1, and positive 2. That means that for L equals 2, there are 5 orbitals. So each set of n, L, and m sub L, those 3 quantum numbers together, describe one orbital. Orbitals with the same value of F are in the same principal energy level. That's the shell, the first, second, third, whatever. Orbitals with the same values of n and L are said to be in the same sublevel. Now they'll have different m sub L's. So let's look at the bottom here. N equals 1. We know that 2 electrons fit in here. One with spin up and one with spin down. So there's one orbital in here. So n equals 1. L can have values of n minus 1, so it only gives it 0. And then m sub L can be positive, negative that, so it only gives it one option. When we go to n equals 2, however, for n equals 2, we said L was allowed to be n minus 1. So it can be 0 or 1. 2 minus 1. So that gives me 2 sublevels. And in each sublevel, the values of m sub L is positive to negative of L. Well, when n equals 0, that's just 0. But when n equals 1, it's negative 1, 0, and positive 1. So there's 4. Well, with 2 electrons in each, that's where 8 comes from. And so on and so forth. So as I said, the number of sublevels within a level is equal to n. The number of orbitals in a sublevel is 2L plus 1. The number of orbitals on a level is n squared. Let's go back. So that means that the number of sublevels in a level equals n. So n equals 1, we had 1 sublevel. N equals 2, we had 2 sublevels. N equals 3, we had 1, 2, 3 sublevels. The number of orbitals in a sublevel is 2L plus 1. So here, 2L plus 1, 2 times L, 2 times 0 plus 1 is 1. 2 times 1 plus 1 is 3. 2 times 2, 5. That works out. The number of orbitals in a level, n squared. So 3 squared is 9. There's 1, 2, 3, 4, 5, 6, 7, 8, 9. True. So each wavelength in the spectrum of an atom corresponds to an electron transition between orbitals. When an electron is excited, it transitions from an orbital in lower energy level to an orbital in higher energy level. When an electron relaxes, vice versa. And this difference in energy is a photon of light being emitted. Now, to transition to a higher energy level, the electron has to gain the correct amount of energy. It can't gain any less than that. Now, whenever they're in higher states, they tend to be unstable. And this should sound very familiar to all kinds of chemical explanations I'm talking about. When they're in a higher energy state, they have more energy. If it's possible for them to occupy a lower energy state, they will. They will transition to that low energy state, and they will emit a photon. Each line in the emission spectrum corresponds to the difference in energy between two energy states. So if we go from n equals 1 up to n equals 3, we absorb that energy. If we go from 3 to 2, we emit that energy. So we can calculate out, using our laws of quantum mechanics, to predict out all the wavelengths of all these different things. So for an electron in energy state n, there are n minus 1 energy states it can transition to. And that's how many lines that electron could generate. The Bohr and the quantum mechanical model predicts these lines very accurately for a one electron system. Albeit we don't always have one electron. So one electron system, we're really talking about hydrogen. So the energy of a photon released is equal to the difference in energy between the two levels the electron is jumping between. So if you're going from energy level 3 to energy level 2, you know how much energy at 3 and how much energy at 2. That difference is how much energy is in the photons being emitted. So just subtraction, final mass addition. Yeah, that should be pretty straightforward. So I talked about earlier that psi is that Greek letter there, the wave function. If you square it, you get probability. So the probability of finding an electron at a particular point in space for an s orbital, the maximum is at the nucleus, decreases as you move away from the nucleus. The radial distribution function represents the total probability at a certain distance from the nucleus. So nodes in the function are where the probability drops to 0. I know it doesn't make much sense. Let's look at the graphs, though. So the probability density function represents the total probability of finding an electron at a particular point in space. And the s orbitals are spherical. So if you look at this, so we're getting the sphere. We got all these dots here for two reasons. One, each dot represents an area we've done a calculation. Two, if we just colored it in, it wouldn't be very interesting. So the density of dots, how many dots are close to each other, is proportional to this function. So at the lower radius, you get a very high density. At a larger radius, you get further and further out. So you're more likely to be close to the nucleus when you're in the 1s orbital. So the radial distribution function represents the total probability of finding an electron within a thin spherical distance at a distance r from the nucleus. The probability to point decreases with increasing distance from the nucleus, but the volume in the spherical shell increases. The net result is a plot that indicates the most probable distance of the electron in a 1s orbital. That's 52.9 picometers. What they're saying is, it might be more likely to find an electron in one of these spaces down here, but there's fewer spaces down there. And it might be less likely to find it out here, but there's so many spots for it to be out there, even though it's less likely to be in an individual spot, there's still a lot of spots. So if you put those two informations together, you can see that there's a maximum right here. The electron's probably right in that distance, almost certainly in this little area right here. That distance is what we call the orbital of where the electron is. Now it could be anywhere in there, but we can see where it's most likely to be. And you can see getting further out here, it drops down to near 0. So if we look at 2s and 3s orbitals, we can start to see these bright spots. This is a really interesting graph to look at, because if we look at this is the probability density and the total radial probability. Remember, the probability density was just squaring the wave function. The total radial probability took into account volume at different distances. So we can see here's the radius, so this is for 3s. Here's the first orbital, there's that sphere. There's the second one, most likely to be in there, and the third one, there. These white spots, these blank spots between the orbitals, those are the nodes, where there's no probability of finding it. Now that's all talking about the quantum number n. Let's talk about the quantum number L. L has energy values from 0 to n minus 1, and it determines shape. So S is spherical, the lowest energy orbital in a principal energy state. So at n equals 1, if L is n minus 1, well, that's just 0. So at n equals 1, then we'll have a spherical. Once we get above n equals 1, we start to get p orbitals with an ml minus 1, 0, and a positive 1. And each of the three orbitals ports along a different axis. On the x-axis, the y-axis, the z-axis. P orbitals are the second lowest energy level, and they're two-lobed. So we get like that. It's like pinching a balloon in the middle. They balloon out like that. So one is aligned along the x-axis, one across the y-axis, and one across the z-axis. If we look at n equals 2, when we get L all the way out to the 2, we get d orbitals. So 4 of the 5 orbitals are aligned in a different plane. A plane no longer means it's an axis. A plane means 2 dimensions. And then the 5th is aligned in a squared region. This is the third lowest energy level, S being lowest, then P, then D. These are 4-lobed, mainly, except that one that's the squared one. That one's a toroid. A toroid is a fancy geometrical term for a donut. So they're planing out on so here's the y and z axis, the x and y axis, the x and z axis. Then here's the x squared minus y squared, which is orienting it much like the xy, just shift. And then the z squared gives us this toroid here. We go up next, now we get f orbitals. These are the 4th lowest. We have S, P, D, and then F. And some are 2-lobed with a toroid. So we get these crazy things. So here this kind of looks like the other ones did. We get them, this weird donut thing in the Z and the X and the Y, and then we start getting these crazy 8-lobed kind of exploding out kind of crystal form. And the geometry, this all makes sense whenever you look at this picture, though. This should be kind of an aha moment for you. Because if we look, these are the ways that all the electrons are trying to be as close as they can to the nucleus, but they're trying to be in these lowest energy states possible, so they're organizing themselves in the different areas of probability so that they maintain the distance to the nucleus that's the most stable without trying to get too far away. And remember what I said earlier, that one of the things that Niels Bohr said is that even these strange predictions that quantum mechanics makes, if you scale it up to the macroscopic and you round it all off, they should follow our macroscopic predictions. So all of these orbitals that were predicted by quantum mechanics, if you look at the average of all of them together, you know what you're looking at, those pictures? That's all of these crazy shapes all put on top of each other. you put all of them on top of each other all at once, they all really do kind of average out to kind of what Dalton said, spherical atom. The atom is basically spherical as an average. So we talked about the wave function. Wave function's positive and negative values. There's nodes where it's 0. The sign would be its phase, so they could be in phase or out of phase. We'll talk about that more about that later. Similar to constructive, destructive interference stuff. So that there's an up and a down part. That'll correspond with our last number there. Some of the stuff is a little bit crazy, but I hope it puts a lot of the basics that you already understood. Now you got some of the why behind it, and that'll make a big difference as we start to use this information to do more analysis to understand other things.